So in this video, we're going to talk about the idea of carbocation stability, right? And so we say that a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation. Now, the reason why we need to know this, especially for organic chemistry, is that when we start talking about 1,2-hydride shift or 1,2-methyl shift, we have to be able to understand the reason why those occur. And so the reason why those occur is essentially because we're getting the carbocation on a more stable carbon. So in this video, we're going to rank these structures A, B, C, and D from the most stable to the least stable, right? Now that means that we already said that a tertiary carbocation is more stable than a primary, than a secondary, which is more stable than a primary. Now, how do we identify them? Well, a tertiary carbocation is on a carbon that contains no hydrogens, right? So a tertiary carbocation would be on a carbon that contains no hydrogen. So out of A, B, C, and D, we can actually see that really two are actually tertiary carbocations, right? Structure C and D, because again, their carbon contains no hydrogens. Right? Yes, we have a CH3, but directly on the carbon, there's no hydrogens. A secondary carbocation, I usually remember it as a carbocation that contains one hydrogen. So in this case, structure A would be a secondary carbocation because it contains one hydrogen. A primary carbocation is a carbocation that contains two hydrogens, right? So on the carbocation, we have two direct hydrogens, and there would be structure B, right? You can see that on structure B, we have a carbon that contains directly two hydrogens, right? So how do we rank these from the most stable to least stable? Well, structured C and D, we both said are tertiary carbocation, right? So how can we rank them? Well, it so occurs that structure D here would actually be the most stable, even though it is the same tertiary carbocation as D and as C, and the reason why is because structure D can actually participate in resonance, right? So essentially, I can move the double bond to satisfy this positive charge on the carbon, and then get the positive charge on the hydrogen adjacent to it. So in other words, if I draw another structure, the resultant resonance structure, what I'm essentially saying is that double bond is going to be placed now here. There's my CH3. There's no carbocation there. However, I do have a carbocation right here. So the idea that it could participate in resonance is the reason why D is more stable than C. And obviously, then it would be true that a secondary carbocation, which would be A, or let me write it in this formula, which would be A, would be more stable than B, which would be the least stable because it is a primary carbocation. So again, it's just a brief understanding of how to recognize tertiary, secondary, as well as primary carbocations.